All right, thanks very much, Dan, and thanks to the organizers of this seminar. I think this is really a wonderful seminar. I'm glad to be able to contribute to it in this way. A couple comments. I put the intended contents of this course up on the screen. So I'll do 4 lectures roughly in these 4 chunks. It's really intended to be kind of a course, so I'll be saying hopefully many basic things as well. It's intended to be sort of understandable for students. So if you are an expert on this stuff, then many parts of this will probably be boring. So bear with me, hopefully. And also, well, I already wrote it. What is not in this course, of course, there are many things that will not be in this course. I can only do so many things in 4 hours. I will not be talking about the unstable atom spectral sequence in the lambda algebra and several related topics. So sorry if you were hoping for that. But okay, let me get started on the first topic, which is rational homotopy theory, which I want to spend most of this first lecture on. And really this, well, this is of course a story that more or less starts with Serre's work. So Serre, 53, well, proved many things, but one very important thing that he proved at that IKSN is, well, is a finitely generated group. Right? So this is finitely generated. Well, of course, it was known to be abelian, but definition of this group for all k and greater than or equal to 1. So in other words, this group really splits as a free part and a torsion group. So this splits the task of understanding the homotopy groups in parts. You want to know the ranks, and you want to understand the torsion. Okay, so if you want to understand these ranks, then you might as well, get rid of the torsion. So tensor with Q, and Serre already computed the result of that procedure. So to be precise, he showed the following result. If you look at the homotopy groups of, let's say, an odd sphere, and you tensor them with the rationals, and this, well, in some sense, it looks like the answer you'd expect if you thought that spheres were Eilenberg-MacLane spaces. So get Q in the degree where it should be, and you get 0 otherwise. Right, so a different way to say this is that the map from this odd sphere to its bottom Postnikov section is a rational equivalence, or is a pi star Q ISO. All right, so that's sort of the simplest possible answer you could possibly hope for, and yeah, it works. For even spheres, the situation is only mildly more complicated. There's just one extra group. So we show the following thing. It's again Q in the expected degree 2n, and there's another pair up in degree 4n minus 1, and 0 otherwise. So in other words, there really is very little sort of torsion-free stuff in the homotopy groups of spheres. Most of it is torsion, of course. All right. So, and the proofs of this, well, of course, in some sense, the method is more interesting than the result here. Well, yeah, okay. It's the Serre spectral sequence, which was clearly developed by Serre, and these are some of the first applications of the Serre spectral sequence that you would do in any course on sort of advanced algebraic topology. Okay, so if all you wanted was sort of to get information about the homotopy groups of spheres out of this course, then we could end this lecture more or less right here and move on to the next one. And well, I guess many people in their exposition also do that. But of course, I want to do a little more. I want to talk a bit more about rational homotopy theory for essentially 2 reasons. So the first reason is, well, there exist spaces other than spheres. And the second reason, which may be a bit more serious, is that the structure of rational homotopy theory that I want to discuss is in some sense a blueprint for some of the techniques that will feature later. For example, when we're looking at the Goodwillie tower on a sphere and how you can think of that as structuring the calculation of the homotopy groups. So rational homotopy theory that I want to talk a little bit about, and I want to make one more comment about this result of Serre before we go there. Here's a slightly more precise statement of the second calculation. So the rational homotopy groups of the even sphere, this pi 4n minus 1 of S2n You can give an explicit generator for it, and it's generated by the Whitehead bracket. The Whitehead bracket of the fundamental class, I'll write that iota 2n of the 2n sphere with itself. Okay, so the Whitehead bracket will play a very important role in this course. It will feature essentially everywhere. So let me just introduce it properly to be somewhat complete. So let's say that X was a pointed space, and I had two classes. Let's say alpha and beta in the homotopy of X. Then the Whitehead bracket of these, or the Whitehead product. So the Whitehead bracket alpha beta. So this is an element in pi k plus L minus 1 of X, and it's given as the following map. So this is the composition. Well, what can I do? First of all, I can use alpha and beta and wedge them together to get a map from this wedge of two spheres into X. Now I'm going to precompose this with a certain, well, in some sense, the universal Whitehead bracket. So it's a map from Sk plus L minus 1 into here. And this map is perhaps most easily described as follows. It's the attaching map of a K plus L cell in the product Sk times Sl. So this is the attaching map of the K plus L cell for the space Sk cross Sl with its obvious CW structure. Okay, so on pi 1 it will give the commutator, of course, but on the higher homotopy groups it gives the Whitehead bracket. So here are some facts about this bracket. The first one is the Whitehead bracket. Well, the bracket notation is suggestive. It really is a Lie bracket. Okay, so the Whitehead bracket makes, well, you have to shift by 1. So if you look at pi star plus 1 of X, this graded abelian group, then the Whitehead bracket makes this into a graded Lie algebra. In other words, it satisfies anti-commutativity in the graded sense. Satisfies graded anti-commutativity. And it also satisfies the graded Jacobi identity. Right? And the other thing about the Whitehead bracket is that it's a very unstable operation. Right? So I had elements alpha and beta, and I took their bracket and I suspended this, then I actually get 0. Okay, so it's really something that is very much in the realm of only unstable homotopy theory. In terms of this Whitehead bracket, you could actually rephrase Serre's result as a result about, well, in terms of these Lie algebras, if you will. So here's a rephrasing. Serre's result. Essentially, his calculation of the rational homotopy groups says that the rational homotopy groups of spheres are the free Lie algebra over Q on the fundamental class. So pi star plus 1 of an n sphere tensor Q. This is the free graded Lie algebra over Q on this identity element iota n. Okay, so the reason that this works, if you, well, you have to think about the degrees a little bit, but of course, if n odd, then the free Lie algebra on one generator is what you'd expect. I mean, normally in the ungraded setting, the free Lie algebra is just, you know, it's a vector space of dimension 1, right? Already the self-commutator of your element will have to vanish by antisymmetry. So here, because of this funny degree shifting, for n odd, you get that this is 0 by antisymmetry. There's nothing else to say. And when n is even, this bracket is not forced to be 0 by the antisymmetry axiom. So this is not 0 in the free Lie algebra. But then all the higher ones are as a consequence of the Jacobi identity. Right? So all higher brackets vanish. So in that case, the free Lie algebra on one generator really is a two-dimensional vector space. Okay. Let's see. So what I want to do is, also because this is going to be important later in the next few lectures, prove a very elementary thing which you might well be aware of. But let me actually prove that the Whitehead bracket of iota n with itself generates that group, right? So let's prove that this element which lives in pi 2n minus 1 of Sn is not torsion when n is even. Just going through this in maybe too much detail because this calculation will actually play a big role next lecture. So the way to do this is classical, and I guess discovered by Hopf originally. It's namely you compute the Hopf invariant of this map to see that it's not torsion. Right, so the idea is you compute the Hopf invariant. So the Hopf invariant can be thought of as a homomorphism from pi 2n minus 1 of Sn to Z. And how do you do it? Well, if you have an element in that homotopy group, right, you view it as the attaching map of a 2n cell. So you build a corresponding two-cell complex with cells that are in dimensions n and 2n. And then if you look at the cohomology ring of that complex, then the generator in degree n will square to something, some integer times the generator in degree 2n, and that integer is the Hopf invariant of the original map. So this is a calculation you can do for the Whitehead bracket quite easily. So if you look at the map, let me give this element a name actually. I'm going to call this Wn, this Whitehead bracket. So I can take this Wn and attach a cell along this map. So take the cofiber X, and now, it's actually pretty easy to think about, to calculate the cup product, because this is really just a quotient, if you think about it, of Sn cross Sn, and this allows for the following calculation. If you calculate the Hopf invariant of Wn, you'll see that this is 1 plus minus 1 to the n. Okay, so it vanishes if n is odd, but it's 2 if n is even. So immediately conclude that if n is even, then Wn cannot be torsion. In other words, it defines a non-zero element of a corresponding rational homotopy group, and therefore it must generate that group. Okay. Maybe a small remark here, which we'll also see many instances of. It's not necessarily true that this Whitehead bracket generates the copy of Z that you have inside the integral homotopy groups, right? So W2n need not generate a Z summand integrally, so inside pi 4n minus 1 S2n, Indeed, if you try to figure this out, this is more or less exactly the Hopf invariant 1 problem, right? So for n is 1, 2, or 4, of course, there exist elements in this group of Hopf invariant 1. And therefore, in those cases, the Whitehead bracket definitely cannot generate the Z summand. All right. Okay. So let me take a step back and talk a little bit about the rational homotopy category. All right, so Serre's calculation, at least it shows that, well, the rational homotopy groups of spheres are completely computable and quite simple. So you might hope that you could get some general understanding of the rational homotopy category as a whole. So let me just introduce the relevant notions real quick. So I want to think of this of rational homotopy theory as a localization of integral homotopy theory. So I'll just explain what I mean by that, because also that is going to be a model for various localizations that I'll want to consider later. So first of all, let's say that we have a map of pointed spaces. And for simplicity, let's work with simply connected spaces. All right, so such a map is a rational equivalence. It's called a rational equivalence. Well, precisely if it's a pi star Q iso, so it gives isomorphisms on rational homotopy groups. If pi star F tensor Q is an isomorphism, or equivalently, you could also test this on rational homology. Okay, so the thing we'd like to do, well, morally speaking, is you want to consider homotopy theory disregarding torsion or ignoring torsion. So the precise way to do that is to, well, invert the rational equivalences. So rational homotopy theory concerns the localization I'm going to use the following kind of notation: LQ S star greater than or equal to 2. Okay, so this, by this symbol here, this collection of symbols, I just mean simply connected pointed spaces. And this LQ denotes rational localization. What is that? Well, you could say it's whatever you get from simply connected pointed spaces by universally inverting these rational equivalences. All right, so let me write that like this. So now I'll leave it up to you to choose how you want to interpret this collection of symbols. There are many ways to do that. Maybe the most basic one would be if you're talking about the homotopy categories on both sides, then what you're doing is really you take the homotopy category of pointed simply connected spaces, and you take all these rational equivalences and turn them into isomorphisms, universally adjoin inverses to all those morphisms. Of course, usually we want to do something more refined than that. So in the context of model categories, you could do such a thing by well, doing a Bousfield localization, a left Bousfield localization. And of course, nowadays, at least my generation, and I guess people after me, are being raised on infinity categories. You could phrase it in those terms as well. It's not really going to matter for anything I'm going to say. Anyway, we're turning the rational equivalences into actual equivalences. In some sense, that's an abstract process, but of course, there's also a more concrete description. So here's an alternative or equivalent description of this homotopy theory. alternatively, well, a space is called rational. So space here still meaning pointed, simply connected. Space X is called rational if all its homotopy groups, which are a priori just abelian groups, are actually rational vector spaces. So if this is a rational vector space for all K, of course, being a rational vector space is a property of an abelian group and not a structure. Okay, so here are two basic facts. Sort of the standard facts that I guess make the theory of localization work. Where every X, every such space admits what's called a rationalization. So rationalization is a map from X, we call the map eta, into another space XQ, which satisfies the following, namely this XQ is a rational space and the second fact is this eta is a rational equivalence. Okay, so every space can be replaced up to rational equivalence by such a rational space, and a consequence of that fact is that you can alternatively describe this rational homotopy category, or this rational homotopy theory, in the following way. I can look at the inclusion of these rational spaces, or inclusion followed by localization. Okay, so I'm writing this for the full subcategory. Of all simply connected spaces on the rational ones. Okay, so there's an evident functor from right to left, and this is an equivalence. Okay, so this I can realize this localization of homotopy theory as a full subcategory of the original homotopy category. Okay. All right. So the point of all this is that the structure of this homotopy theory can be completely described in algebraic terms. And that turns out to be a very powerful device. So the original version of this is due to Quillen in a paper from '69. And he showed that, well, there are two ways of algebraically describing rational homotopy theory. So there are equivalences. Let me phrase it as follows. Equivalences of homotopy theories, and then again, you can choose for yourself how you want to interpret that phrase. Of course, for Quillen, it meant Quillen equivalences of model categories, although I guess he was using a different term. As follows, so there is this rational homotopy category, and then there are two functors, two different algebraically flavored categories. Let me denote these functors by CQ and LQ. So one of them goes to something having to do with differential graded co-algebras. So I'll denote it like this: co-C-alg in chain complexes over Q greater than or equal to 2. So what does this mean? Well, so these are simply connected differential graded commutative or co-commutative, but let me drop the co, there's enough of that, co-algebras over Q. And the other model is in terms of Lie algebras. So we denoted Lie chain complexes over Q greater than or equal to 1. Okay, so these are connected DG Lie algebras over Q. Right. And these functors, well, they're kind of hard to describe very directly. I mean, if you read Quillen's paper, there are long chains of equivalences between various different homotopy theories. So it's not so easy to unravel, but on an informal level, it's not so bad. This CQ is really a version of the rational chains. So this CQ is a version of the usual rational chain complex. So by a version of, I mean, this functor is definitely quasi-isomorphic just as a function into chain complexes to the usual rational chains. But of course, one of the issues with rational chains is, well, they form a co-algebra, but not actually a co-commutative one, right? So that's one of the things that you have to fix. But at least on the level of homology, this thing does exactly what you expect it to do. So for example, the homology of CQ of the space X, this is just the usual rational homology of X. And well, the CQX is a co-algebra, so we get some co-algebra structure on the homology, and that is the usual one, right? So the co-algebra structure is the usual one induced by the diagonal map of spaces. Right, so that definitely equips the homology with a commutative co-algebra structure. So, well, the existence of such a functor, apart from this subtlety with, commutativity, is maybe not surprising. The other functor is a little more, well, I wouldn't want to say outlandish, but maybe more unexpected. So this function to Lie algebras, this has the following properties. Let me just write it. Not so many words. So the homology of this other functor doesn't capture the rational homology groups of X, but it captures the rational homotopy groups. Okay. So this one actually computes pi star, well, with this shift, pi star plus 1 of X tensor Q. Right, so in some sense, this LQ is a refinement of the collection of rational homotopy groups. Right, you can think of the rational homotopy groups under the Whitehead bracket as a functor into graded Lie algebras, and this LQ goes into differential graded Lie algebras. And the bracket, okay, so the Lie bracket really is the Whitehead bracket. Okay. All right, so we have these two models. Well, a priori, Quillen's result is sort of an abstract result, but I'll discuss in a bit that it's a very practical result that really, together with what Sullivan did after Quillen, really gives you a lot of calculational strength to deal with rational homotopy theory. But it's worth pausing just at the statement of this theorem because I still find it a very striking result. I mean, it's been around for a while now, but the fact that you can translate this portion of homotopy theory completely into algebra, it's something that, well, over the rationals, maybe you should expect something like that. But in general, you don't expect to be able to translate homotopy theory actually into algebra, right? I don't know. I find it an inspiring result. What I want to do is, rather than delve further into this or try to explain why it's true, I want to talk a bit about Sullivan's approach, which is very concrete and very well suited to calculation. Okay, so what Sullivan did is, I don't know, maybe he looked at Quillen's paper and thought, oh, these functors are too complicated, there's got to be something better. I don't know how he came up with it, but what he does is he constructs a very direct functor that's usually denoted APL from spaces, maybe spaces op, to CDGAs over Q. So keep using the same style of notation. So this here really means, and this is really like no fancy infinity stuff. You can really think of this as just an actual honest functor from simplicial sets op to CDGAs over Q. which is a model for the rational cochains. And okay, so the same comment as before applies. I mean, the rational cochains, those are a differential graded algebra over Q, but not a commutative one. This thing that Sullivan does sort of fixes that problem. Like he chooses a model for this functor. He constructs a model that actually does land in commutative differential graded algebras. So the essence of his construction, essentially what he does is he builds a version of the de Rham complex. He builds a version of differential forms, but a version that, well, first of all, takes coefficients in, has coefficients in Q and works for any simplicial set, not necessarily a manifold. So the idea is just to assign to a simplex delta n, you assign, well, you'd like to say sort of the polynomial, the algebraic de Rham complex on the simplex. Well, the simplex itself is maybe not quite an algebraic variety, but there's an evident algebraic analog. So what he does is he assigns the algebraic de Rham complex of, well, I think people like to call this the algebraic simplex. So what you do is you take the hyperplane inside n+1 dimensional affine space defined by the equation that the sum of the xi's should be 1. So it's the de Rham complex of this thing, which is just isomorphic to n-dimensional affine space. So maybe more concretely, it is the complex, or the CDGA. So this is the CDGA described as follows. Well, the usual notation in this business is to use a lambda for a free graded commutative algebra. So this is the free graded commutative algebra on these generators x0 up to xn, and then, well, you have their differentials. Right, so here the degrees of the xi are 0, and the degrees of their differentials are 1, and then you have to mod out by these defining relations. So the sum of the xi's is 1, and then, well, necessarily the sum of the d of the xi's should be 0. All right, so this is what you assign to a simplex. It's just a very explicit CDGA that you can assign to a simplex. And then you also know what to do for every simplicial set just by Kahn extending. Right? So now you take a Kahn extension. In this case, it would be a right Kahn extension because of the op to all of spaces op, and that's the functor APL. That Sullivan constructs. And so the theorem, which is close to, well, the coalgebra version that I already stated, is that, well, this functor induces an equivalence of homotopy theories from these rational spaces that are simply connected, but now I have to introduce an extra hypothesis because I'm dualizing. I'm going from chains to cochains. So I'm taking linear duals of vector spaces somewhere. So I'll have to restrict to spaces that are of finite type. Okay, so this means finite type. In other words, in every fixed dimension, the rational homotopy should be a finite dimensional vector space. Okay, so this APL functor, it goes from here to these CDGAs over Q. So these will also be simply connected and of finite type. And the theorem is that this functor is again an equivalence. Right, so the strength of Sullivan's result is not this particular statement that I'm making here, because in some sense this is also contained in Quillen's statement already. It's the fact that he constructs this very explicit functor that you can get your hands on. And what's more is he came up with the method of minimal models, which is really what makes calculations go. So talk about those a little bit. By the way, feel free to slow me down with questions. I'm noting that I'm talking a lot. Like in an actual lecture, you have more natural pauses when you have to erase the board and things like that. But,
yeah, let me second that. You can rate there. You could raise your hand. You could just chime in. You can post a message in the chat. Various ways that we can interact with the speaker. We'll also have plenty of time at the end for more detailed questions as well.
thanks. Be surprised if there are 100 people here and no one has a question. That'd be bad. All right, let me talk about minimal models for a bit. Here's the definition. Let's say that I have a simply connected CDGA A over Q. So such a thing is called minimal if it satisfies the following conditions. So this is minimal if, well, first of all, the underlying graded commutative algebra, just forgetting about the differential, is free. That's condition 1. Okay. So in other words, is of the form lambda v with this lambda notation I was using earlier for some graded vector space v. So this just means it's polynomial on the even generators and it's exterior on the odd generators. The second condition is the following. If I take the differential on one of these little v's that lies in this vector space, capital V. So if I take a differential of a generator, then this is decomposable. So this is decomposable for every little v in capital V. In other words, you can write it as a linear combination of products. Okay. So these minimal algebras, these minimal models will be useful because they're very small and you can explicitly determine them in practice. So let me list a couple of facts. Well, 3 facts actually. First of all, any A admits a minimal model. What does that mean? That means there exists a quasi-isomorphism M to A, so morphism of CDGAs with M minimal. All right, the second one is these minimal models are unique up to isomorphism. Oops. Unique up to ISO. And then the third one is, well, if you had 2 spaces, X and Y, then these are going to be rationally equivalent if and only if you can find an isomorphism between their minimal models. So minimal models, MX, and again, I'm assuming simply connected finite type, etc. in the setting of the theorem that I stated, are isomorphic. So when I say minimal model of a space, I mean a minimal model of APL of the space of the associated CDGA. All right. So let me just give you some examples. So here are examples of such minimal models that should make clear how concrete this is. Let's first do S2n plus 1. Well, of course, the cohomology of S2n plus 1 with rational coefficients. Well, it's like the cohomology of a sphere is always a square 0 algebra. The generator always squares to 0. But if the generator is in odd degree, that's the same as being free. right? This is an exterior algebra on, I was calling it iota. Well, I guess I was using it for something else, but we just use iota for fundamental classes generically. This is free as a CDGA. So first of all, that makes it very easy to find a map. From this into, well, any model for the cochains. So APL of S2n plus 1. And this is a quasi-iso. It's a quasi-isomorphism. So in other words, this thing here is already a minimal model. So this is a minimal model for an odd-dimensional sphere. Right, so that's sort of the easiest possible case. And the case of an even sphere isn't much worse. Here, well, if you want to find a minimal model, you could start in the same style. You could start by looking at a free algebra generated by a class in degree 2n. But now it's in even dimension. So of course, this will generate a polynomial algebra. So you have to do something to kill off the higher powers of iota, which do not appear in the cohomology of Sn. We can't actually take a quotient of this algebra, and the algebra itself has to be free. So the way to kill the higher classes is, of course, introduce another one and a differential. So there has to be another class here in degree 4n minus 1. And the differential is determined by declaring that d of this y is equal to iota 2n squared. Okay, so iota squared dies in cohomology. Now we've constructed a minimal model. Let's see. Okay, so I've constructed a minimal CDGA in this case, and it's reasonably easy to see that you can map this thing into APL of S2n. Namely, what do? Well, first of all, you send iota 2n to any representative of that class, of the fundamental class. And because the square of that class vanishes in the cohomology of APL, there must be some y that kills it by a differential. So you pick one and you send your y there. So it gives you a morphism of CDGAs, and it's a quasi-isomorphism by inspection. So in other words, this here is a minimal model. All right, for S2n. All right, so there was some stuff going on in the chat. Let me just check. All right, I'll try to wait at the end of the page. I hope I'll remember. If indeed this is recorded and distributed later, you won't actually have to copy anything, I think, but okay. All right, so these are the simplest example of minimal models. And I mean, if you've seen this before, then of course you know this. If you haven't seen this before, it's really fun to just try to play with some basic examples and see if you can find minimal models, because it's a very concrete game, like complex projective spaces, compact Lie groups, things like that. Okay, so Sullivan's approach, this whole approach with these piecewise linear differential forms is really closely related to cohomology, right? You always start with the cohomology or the cochain complex of your space and then try to build a minimal model for it and understand the rational homotopy type in those terms. So it's maybe not immediately clear how you talk about the rational homotopy groups of a space, but also those can be easily extracted from a minimal model. So let me talk a bit about the rational homotopy groups of spaces from this perspective. So here's the key results. Let's say again that X is simply connected, pointed, etc. And let's say that I fixed a minimal model. So it's some pre-algebra, a minimal model of APL of X, then the claim is as follows. The rational homotopy groups of X can be extracted as follows, or rather, I can extract their duals. So let me use this check to just denote the linear dual. Namely, these are just the vector space V, just the generators of this algebra. Okay, and moreover, you can also extract the Whitehead bracket. Let me state it as follows. The differential D is dual to the Whitehead bracket. It's maybe a slightly informal statement, but as I said, for a minimal model, the differential will go from V into the decomposable elements. So you could look at that part that just consists of sums of products of two things. So you look at the two component of D, so to speak, and that is really the dual to the Whitehead bracket on the rational homotopy groups under this identification that I put here. Okay, so also the Whitehead product you can read off from a minimal model. One example of this is if you now apply this to the minimal models for the spheres that I just described, you get exactly the result of Serre's theorem. So applying this to the minimal models of Sn that I described above recovers Serre's calculation. Right, so in the even sphere case, it's exactly this extra y4n-1 that we had there that will account for the class in that dimension. And if you, well, just the fact that its differential is exactly the fundamental class squared is encoding the fact that the Whitehead bracket of the fundamental class with itself is, well, the dual of this yn, okay? So that's one way to think about that calculation. So what I want to do is I want to put this sort of going back and forth between cohomology and minimal models and rational homotopy groups a bit into perspective, because precisely that procedure will be a blueprint for some calculational devices that I'll be looking at later, particularly results of Barron's rest.
Sorry, can I ask a question first?
Yeah, of course.
Yes, so on the previous page, if you can just go back. So you say, yeah, this one. Yeah, you say applying this recovers Serre's calculation. So is this actually, you know, a separate proof of Serre's calculation, or does the setup use Serre's calculation in order to get things going?
I think what you use to get rational homotopy theory going is the calculation of the rational cohomology of Eilenberg-MacLane spaces and the Eilenberg-Moore theorem to induct up the Postnikov tower. I think those are the two formal ingredients that you need. So you don't need to calculate the rational homotopy groups of spheres, although, of course, I mean, yeah, I say it recovers Serre's, if you just wanted the result of Serre's calculation, of course, you're not going to go through all of that. I mean, because the argument that computes the rational cohomology of Eilenberg-MacLane spaces is not, like from there, it's not a long step to get to Serre's calculation, obviously. So there's one more thing you have to do. There's one more Serre spectral sequence you run. So I wouldn't advise this as an exposition. I'm just saying, you could interpret it as a separate proof, but maybe that's a bit, yeah.
Okay, thanks.
Yeah. All right, I hope that answers the question.
Yes.
Okay, cool. All right, so I want to talk a bit about this back and forth between Lie algebras and commutative algebras. So one thing to note about this statement, I said the rational homotopy groups of corresponding to a minimal model are just the vector space V. One way to interpret this vector space V is, well, as the generators of this thing, but I really want to think of it as the indecomposables, which for free algebras is the same, but in general it's not. So these are the indecomposables. Of this free algebra with minimal model X. So what I want to do is just give a slightly more homotopy invariant statement of the thing I just said that doesn't need to pass through a minimal model. So if you want to do that, then, well, you have to consider the derived functors of indecomposables. So those have a name. Those are called André-Quillen homology. So André-Quillen homology, by definition, this is the derived functor, or maybe the collection of derived functors, depending on your conventions, of this indecomposables functor. Right, so what does that mean concretely? If you wanted to compute André-Quillen homology for a general CDGA, then what you have to do is you resolve it by free ones. So you compute by taking a simplicial resolution by free CDGAs, sorry, free CDGAs and taking indecomposables degree-wise. It's just the general pattern of derived functors, maybe non-abelian derived functors. As a phrase like that, you could say the following. So here's a sort of homotopy invariant formulation of the proposition that I had on the previous page. You could say that the duals of the rational homotopy groups of X are exactly these André-Quillen homology groups of this CDGA APL of X. Okay, I mean, there's not much content to this generalized statement. I'm just, it's just a homotopy invariant way to say it, but I want to stress this a little bit because it will allow me to say something that I do find useful. Namely, the complex that computes André-Quillen homology can be upgraded to be not just a complex, you can really make it a Lie algebra, or well, you have to dualize it first. André-Quillen cohomology, you can make it have values in Lie algebras. So I'm going to the next page. Let me just pause for 5 seconds.
Could you sketch proof of the previous proposition?
This one?
Yeah.
Is that okay? You just wanted to see it, right?
Oh, if you can sketch a proof of it.
I don't want to do that right now. Let me get back to you, okay?
Okay.
I mean, okay, I will sketch a proof of it. If you wanted to compute the rational homotopy groups, what you have to do is you have to compute homotopy classes of maps between your minimal model and the minimal model for a sphere. By this equivalence of homotopy theories, you can compute homotopy classes by computing homotopy class maps between CDGAs. And because the minimal models for spheres are so simple, it's not hard to analyze those homotopy classes explicitly. And you can see that if you map from a minimal CDGA into the minimal thing for a sphere, you get exactly this result. I think that's a sketch of proof.
Thank you.
You're welcome. So, okay, what I wanted to say is this André-Quillen cohomology, by which you just mean you take the homology and take the linear, or the complex computing homology and take its linear dual. This is part of an adjoint pair as follows. So, as I was just saying in words, this André-Quillen cohomology, so I'm going to denote the cohomology also by this little check up there to indicate the dualization. Well, a priori, it takes values in chain complexes over Q, but it can be upgraded to, it has more algebraic structure, namely that of the Lie algebra. So this is really a functor that you can, if you construct it carefully, have land in differential graded Lie algebras over Q. And as such, it has a left adjoint, at least on the level of homotopy categories, or if you, depends a bit on your setup. And this left adjoint also has a familiar and explicit description. It's really Chevalley-Eilenberg cohomology. So this is Chevalley, Eilenberg cohomology. And this, at least in its usual construction, its usual definition, really is a CDGA, so that's good. And one way to think about Chevalley-Eilenberg the construction of Chevalley-Eilenberg cohomology is very much dual to what I was talking about with these derived indecomposables. Like Chevalley-Eilenberg cohomology or homology is also really the derived indecomposables in the appropriate sense. So this is really the derived functors of abelianization of a Lie algebra. And abelianization that is, well, I would call that indecomposables of a Lie algebra. So this is really a two-way street, and in both directions you're taking the appropriate notion of indecomposables. But a slightly nicer statement is to do it as follows. I want to get rid of finite type stuff, so I don't want to be, I don't want to be taking linear duals everywhere. So as usual in homotopy theory, if you want to get rid of finite type hypotheses, at some point you have to trade commutative algebras for commutative co-algebras, or something like that. And that also works in this case. So there's really an analogous adjoint pair that takes homology, Chevalley-Eilenberg homology rather than cohomology, and this lands in commutative differential graded co-algebras over Q. Okay, so this is now Chevalley-Eilenberg homology. And the adjoint, well, it's now some dual construction to derived indecomposables. I'm not sure there's standard notation for it. I'm just going to call it prim. So this is the derived functors of primitives of coalgebras. So these you would compute by taking a co-simplicial resolution of your coalgebra by co-free guys, taking primitives degree-wise, and then totalizing. Okay, so this adjoint pair, the good thing about it is, and in some sense, well, in a precise sense, I mean, this is due to Quillen. This is in his rational homotopy theory paper. This restricts to an equivalence between appropriate subcategories, namely those of connected DG Lie algebras and simply connected DG coalgebras. So this is one way to approach Quillen's theorem if you wanted to. Like you could first go through Sullivan's story and prove the equivalence with appropriate CDGAs or differential graded coalgebras, and then invoke a result like this to get from the coalgebra model to the Lie algebra model. But this being able to go back and forth between models is very useful and very important, and it will feature quite a lot in later lectures. So this nowadays is nowadays people usually refer to something like this, an adjoint pair like this, as Koszul duality, or this is a specific instance of Koszul duality, namely applied to Lie and commutative algebras. It wasn't called that in Quillen's paper, but he already recognized exactly this. Right, I think now is actually a good time to field some questions.
Right, okay, so hang on a second here. What am I doing? I'm going to unmute everyone, first of all, so that we can thank Gijs. Okay, and